The one is related with the precipitation hardening. So for this, like the T6 or T4 kind of the heat treatments are used. These are mostly used for the precipitation hardenable alloys. And another aspect about which I want to talk is like that the fundamentals related to the heat treatment of hardenable steels. Okay, so these are the two important aspects I want to talk. So the precipitation hardening is based on the simple principle of developing fine, well distributed precipitates. These can be of variety types, different types of the precipitates depending upon the alloy systems. And these may be of say nanometer, or hardly you will find they are of the micrometer. Mostly these are very fine. And the typical one, like say in aluminum, magnesium, silicon alloy, Mg2Si is one. In aluminum copper alloys, CuAl2, okay, and MgZn2 in aluminum, zinc, magnesium kind of the alloy. So depending upon the kind of the alloy, you get the different types of the precipitates. To form these, so what is the principle on which it works in, like say these are the grains and you have got fine precipitates here and there. So these precipitates resist the movement of dislocations. Say a particular slip plane, as soon as their dislocation come across the fine precipitates, their movement is restricted or resisted. So movement of dislocations is resisted by these fine precipitates. So when these are fine and well distributed, they are more effectively able to check the movement or stop the movement of dislocation. So they are able to resist the deformation, which in turn helps to increase the strength. That's logic. When they are you see, so this is what happens when your the precipitation is of the desired type, which means the peak hardening situation or state has been realized. When you have the under age hardening or under hardening situation, you will find that there are very few precipitates here and there. And when you have got the over hardening or over aged situation of the hardening, you will find that these few so initially they were, so we go through the situations like under age hardening, peak age hardening, okay, and third one over age hardening. So these are the three things, situations through which so when it is underage, there are very few dislocations here and there. When they are peak age hardened, you will find very fine distribution of the fine precipitates within the grain. And in overaging, all these fine precipitates are consumed and you find very few coarse precipitates, okay, in over age hardening situation. So you get the maximum below this, the situation happens like this. So this is the over age situation, this is under age hardening situation, this is the peak age hardening situation, okay. So what we want, like these are hardened for the peak hardness. It can be under in both the cases. When it is underaged or overaged, the hardness is lower. That's what you can see in these two cases. So what is the prerequisite for the precipitation? prerequisite for precipitation is very simple. Like it mostly happens in case of the precipitation hardening happens in case of the alloys. Say, so there is a matrix and there is alloying element. Okay, so the relationship with regard to the solubility of the alloying element in the matrix should be dependent on the temperature. The solubility should vary with the temperature. So that's the kind of relationship. Like say A is the matrix and B is the alloying element. Solubility of B in A should increase with the temperature, and that's what we show here. Like say the alloying element with the increase of, here we have y-axis, we have temperature, and here you have alloying concentration. So the solubility keeps on increasing like this with the increase of temperature. This line is known as solvus line, which is indicating the variation in the solubility as a function of temperature of the alloying element. So say a particular concentration of the alloying element is say 2% here. Okay, say La 2% B. Okay, so here it will have certain kind of the precipitates, phases, compounds, whatever it is. When these are heated, you will find that these will tend to get dissolved completely above after reaching a certain temperature as per the composition. So for 1%, say here above this, every alloying element, all the alloying elements will be able to get dissolved. And so the temperature above which all the alloying elements will be getting dissolved in the matrix, that is indicated by this solvus line. Okay, and so means increasing the temperature, you will see that the things are getting dissolved, and below that they are getting rejected also. So at the low temperature, when it say A is rejecting B, it may form compounds, it may form certain specific individual phases like that. So or these may form a particular kind of the precipitates. Okay, so that will depend upon the condition which are provided to the alloying element. Okay, so what kind of the thermal cycle we try to follow in the precipitation hardening to form the fine precipitates. See, we go through this simple cycle. Say this is solvus line, this is the like say a particular phase diagram of a metal system. So alloy composition is this, and when you heat it up to this temperature, so everything get dissolved. So when the heating of an alloy is being done to form the homogeneous solid solution, when this is being done by heating to the high temperature, this process is known as solutionizing. Okay, once the homogeneous solid solution has been formed by heating to high temperature for sufficient time, say for most of the aluminum alloys it may range say from 450 to say 530 degrees centigrade or so. It is lower than 550 degrees centigrade. So heating to the high temperature for sufficient long time will be leading to the dissolution of all the alloying elements which is present. Say B element present in A will be forming the solid solution, homogeneous solid solution. Okay, since this is at a high temperature where you see it can dissolve more, this is the solvus line, which means at this temperature it can hold this much of the alloying element, at this temperature it can hold this much alloying element. So basically you are forming the solid solution at a high temperature. If the temperature is too high, it may not be super saturated, it will accommodate all the alloying elements. So this is the temperature at which when the alloying elements getting dissolved and forming the saturated solid solution. Above this it will be undersaturated, okay, and below this it will be oversaturated. So the variation in temperature, change in solubility as a function of temperature is crucial in precipitation hardening. So what we are doing, the LOI is being taken and it is being heated so that it forms the solid solution, homogeneous solid solution. Thereafter what we do, we quench it rapidly. Okay, second step. So quenching. So the the alloying element which had formed homogeneous solid solution at a high temperature, when it is quenched, everything is retained wherever whatever is present. So no time for diffusion to take place, and that is what will be leading to the formation of super saturated solid solution, because you are forcefully trying to put the alloying elements in the matrix without by not giving enough time for diffusion to take place. So it forms a super saturated solid solution. So after solutionizing by heating to the high temperature for sufficient time, which may range from say 30 minutes to 1 hour, that's very common, and if it is the casting of the very large size, it may keep on adding, say 30 minutes will keep on adding for each of the 1 inch section. Okay, so after solutionizing, it is the rapid cooling or quenching to form the supersaturated solid solution. Once the supersaturated solid solution has been formed, it is reheated. So what we are following the cycle, heating to the high temperature, solutionizing, followed by rapid cooling. So this is the quenching phase, this is the solutionizing stage. Okay, and after this quenching to the room temperature, here you get the super saturated solid solution, and here you get the homogeneous solid solution. Okay, the difference is in the homogeneous solid solution may be undersaturated because of the high temperature exposure. In y-axis we have temperature and in axis we have time. Okay, thereafter we heat it again to somewhat higher temperature, which may range say from 120 to maximum 200 degrees centigrade for most of the precipitation hardenable alloys like the aluminum or magnesium kind of thing. So here whenever it is reheated, this super saturated solid solution starts forming the precipitates because the alloying elements start getting rejected in the matrix, and there it will start forming the fine precipitates here and there in the matrix. So initially you had a few constituents here and there. Okay, when you heat it, everything gets dissolved, so you get basically all the constituents where in the alloying element was present in form of different phases, individual constituent or some kind of the compound, so that gets dissolved. So here you are getting homogeneous solid solution. Okay, and when it is cooled rapidly, everything whatever was present, everything will be present here and there in form of the alloying element, which is more than its solubility limit. Once it is reheated, the fine precipitates starts getting formed in the within the grains. So that is how the solid solution strengthening happens. There are 3 stages. One is solutionizing, second is quenching, and third is like say aging, high temperature exposure. Aging can be done at room temperature also, but it takes very long time, while when artificial aging at a high temperature is applied using artificial aging, it is called artificial aging. So natural aging at room temperature and high temperature exposure if given, we call it as artificial aging. Okay, so how the things change as a function of the temperature during the heat treatment. So here if we have the time, and here we have temperature as far as aging is concerned. So if we give very high temperature exposure, here we have the hardness, the way by which strength will be changing as a function of time during the aging. Okay, variation in hardness, say HV, as a function of aging time, which may be artificial aging or natural aging. So we'll talk about the artificial aging particularly like this. Okay, so what happens when we say it was already solid solution supersaturated, it was a supersaturated solid solution which will have some hardness, supersaturated solid solution after quenching. Okay, so when you give the high temperature exposure, hardness increases rapidly and then it comes down like this. So this is say happening at 200 degrees centigrade. Okay, when you heat little lower temperature, it will be taking longer time to reach the peak hardness. Say this is happening at 120. So further, when you use the lower temperature of exposure, it say 150 degrees centigrade, it takes further longer time to reach the peak hardness and then it starts decreasing like this. Okay, so this is say 130, and now this may be in this may be say just 1 hour. Okay, this may be 180, it may be peak temperature, peak hardness is being achieved say after 2 hours. Okay, here it may take 6 hours, and here it may take even 60 hours. So very long time it may take when very low temperature is used, and when say it is room temperature, it may take like say 10 days to 15 days when it is say done at 24 degrees centigrade. That's the room temperature. So in these cases what we'll see, the hardness will keep on increasing first and then it starts decreasing after reaching the peak value. Same is happening at all hardening temperatures, all aging temperatures. Okay, so the typical curve in all these cases is of the same type. First it increases, then it starts decreasing, and that is what we can understand from this typical variation. Like say the hardness first increases then decreases as a function of time. Here we have the hardness variation. So so this is the peak hardness, you can say the pH or the peak hardness situation. Okay, and this is the time required for achieving the peak hardness. Below that we will find that the precipitates being formed are less. That is why initially there is a continuous increase in the hardness with the increasing precipitation as a function of time. So here you may had very few precipitates here and there, and in this after this much time you may have little more precipitates. Okay, fine precipitates here and there. So this is the difference. So this is the underage stage. In underage stage, hardness is lower, where the hardness will keep on increasing as a function of time during the aging process. After reaching the peak hardness value, you will find that here fine precipitates very well distributed in the matrix, able to effectively resist the movement of dislocations, and therefore it is offering the good hardness and strength like this. After this, if you continue to heat for further longer time than desired, then you will find that fine precipitates starts getting clustered. Their coarsening will start by consuming the fine precipitates here and there. So this is and this situation will keep on increasing as a function of time. So since the coarsening of the precipitate has started, their numbers will keep on decreasing. So that in turn has resulted in the overage stage. Overaging. Okay. So in overaging and underaging, in both the cases your hardness and strength will be lower. That is why efforts are always made to identify the time for the peak hardness, peak strength. Okay. So this is this is what typically happens in all precipitation hardening metals. Now I'll show you a certain PPT, say these diagrams, just to make the things more clear. Okay, about all these things I have already talked. Like say this is a typical phase diagram. This is the solvus line. Okay, which is indicating that how the solubility is changing as a function of temperature. This is a alloying element, and this is the temperature, okay, in the y-axis. So here let's say the alloy of particular composition, when it is heated like this, here it forms the like the alpha matrix and some kind of the precipitates which are there. So everything gets dissolved and forms the alpha matrix. Okay. So this temperature is say may vary depending on the composition. It may be like say 450, 500 or more, 550, or also depending on the alloy composition. Okay. What is happening here, that's what schematically has been shown here. Initially you may have these precipitates and the phases here and there at the grain boundaries. When you perform the heating from the room temperature to the high temperature, everything gets dissolved. So here everything is getting dissolved and you are having the just the grains only, where whole of the phases, constituents, individual ingredients or the compounds, all everything has been dissolved. Thereafter what we do rapid cooling. So on rapid quenching, all the solutes wherever they are retained. So because you don't have enough time for the diffusion to take place, so a thermal this is a thermal process or diffusionless process where leading to the formation of the super saturated solid solution at this stage. Thereafter we start heating and hold it at high temperature for some time so that fine precipitates are formed. So that's leading to the fine precipitates within the grains are formed on the cooling, and thereafter we cool it slowly. Okay, so this is the typical cycle, and let me see if I can erase. Okay, so this is what I have already just explained. Say this is the same Solves line. Okay, so what we are doing, like when the homogeneous solid solution is formed, you quench it. On quenching, your matrix with the super saturated solid solution is formed without any presence of any specific constituent, and then you give the exposure to the high temperature so that the very fine precipitates are formed, and this is how you can see. And when the precipitation continues for a little longer time, the coarsening of these precipitates take place. That's what I have shown here, the coarsening. The solution treatment, rapid quenching or supersaturated solid solution formation, and thereafter peak hardening leading to the fine precipitates, and finally the coarsening on the overaging. Hello. So this is what you can say. This I have already explained using this diagram just now and before. So this is the hardness as a function of the aging. So here underaged situation, that corresponds to like say the heat treatment T3 and T4 kind of thing, where like say in the natural aging it takes very long, maybe months or weeks, so hardening will continue. That's why it is termed as the T4. That's the underaged hardness situation, and the peak hardness is the range of time where that corresponds to the alloy. That depends on the alloy system actually. So here the peak this is the peak hardness situation corresponding to the this is corresponding to the peak hardness. Okay, that's the T6 heat treatment, and then overaging you get the reduction in the hardness. So the same thing I was talking about, like when you use low temperatures. हाँ अभी क्लास में मैं बाद में बात करूँ. Okay, so these are the different things which are formed on the aging. Say when you use a high temperature, your peak hardness is achieved earlier and then it starts decreasing. Okay, and that is primarily attributed to the formation of the GP zone 1. Okay, and when you go for somewhat lower temperatures, it takes longer time to reach the peak hardness. So initially GP zone formation and then GP zone 2 types of the precipitates, Grunier Preston phases, basically precipitates which are formed on the heating at a higher temperature, means for longer time. So you can see here it takes actually the very long time when you use a very low what you can say very low temperatures. Okay, it can take very long time to reach Okay, this is another diagram which is just showing the way by which things change. So supersaturated solid solution hardness is this much. When you use higher temperature, this is what happens. Further higher, lower temperatures, this is what you are. So with the increase of the temperature, your with the reduction in temperature, your peak hardness is increasing, and the time required to reach the peak hardness is also increasing. Okay, that's what you can see in all these cases. These are the two main things. So increasing the temperature is decreasing the peak hardness or peak strength that can be realized. One, it decreases the time that it takes to reach the peak hardness. These are the two important things. So underaging and overaging will be happening accordingly in the system. Okay, when you use a very low temperature, say 30 degrees centigrade, you see there is no change for a long time, and then it starts improving. So depending on the LOI system, it may take really long to reach the peak hardness. Okay, so most of the time efforts are made to optimize the, like say, and aging time, so that you have the maximum hardness and the strength corresponding to the peak hardness. Okay, otherwise below that you will have the overaging. In all these cases, these are like overaged situation, and after that you will have the here underaging, and this side overaging. So both are actually not good for the hardness and strength as far as the heat treatment is concerned. Okay, so that was about the you can say the heat treatment, the T6, or the heat treatment which is used for the precipitation hardening purposes. Okay, so it is not for a particular metal. The similar principle is used for titanium, stainless steel, or the aluminium and magnesium alloys, copper alloys. Of course, with the change of the metal system, the temperature values and time values will change, but in general principles, in general things remain same. Okay, now coming to the heat treatment of steel, and whatever now I will be talking about as far as the heat treatment of the hardenable steel is concerned. Hardenable steel. When we say that steel is hardenable, any idea of? Anybody comment?
Sir, it is a transformation quenching.
No, you see, the change in hardness and the strength can take place when you have like ferrite perlite, which are coarse, and during the normalizing, okay, you may get the fine ferrite and perlite. Even then you will find, say, change in hardness from 15 to 20 RC. It is taking place, say 25 to 30 RC. My point here is, in this case there is no change of phase, there is just a grain structural change. So there is no basically transformation hardening. For the transformation hardening or hardenable steel means you are trying to exploit the change of phase from austenite to, say, you are forming martensite or benite or mix of martensite plus perlite, like that. So when you are having some martensitic transformation or martensitic benitic transformation from the austenite, and that is if leading to the change in properties, then we'll say that this is like hardenable steel. Okay, and this is not characterized in such a simple way. We use one simple parameter that is called carbon equivalent. That is an indicative of the like say ease of hardening, ease of hardening or transformation. And how do we relate it? We relate it with the with your CCT diagram basically. So in CCT diagram, what you have, yours the curve in the CCT diagram, continuous cooling diagram, in the x-axis you have time, in y-axis you have temperature, and say this is the austenitic temperature. Okay, say L1, you see lower critical, LCT, you can see lower critical temperature of 730. Okay, so the minimum cooling rate for 100% moderate transformation corresponds to this one. Okay, this cooling rate may be like say 7 degree or 10 degree centigrade. Okay, for this particular steel. Okay, if your steel composition is say 0.8% carbon, if 0.8 carbon plus you are having some other alloying element, so then there is a possibility that this curve may get shifted to some other side like this. In that case, your critical cooling rate requirement may get modified significantly like this. And now the critical cooling rate required may be just 4 degrees centigrade per second. Okay. On the other hand, if your what you call if your okay, if your the carbon content is reduced, alloying elements also have been reduced, you may find that your these lines have got shifted towards the left side, and the critical cooling rate requirement has changed accordingly. Now this may be like say 30 degrees centigrade per second. The point here I am trying to make is the alloying elements in the steel dictate the these transformation lines in the CCT curve, which in turn affects the critical cooling rate. Higher concentration of the alloying element and higher concentration of the carbon content leads to the lower critical cooling rate. It instead of say 30, it may be just 5 degrees centigrade requirement for transformation of austenite into the martensite. Okay, so how to account for this the role of the alloying element? To account for the role of alloying element on the critical cooling rate and accordingly so on the ease of transformation is linked with the carbon equivalent. So carbon equivalent is a parameter CE which accounts the effect of all alloying elements, which accounts the effect of alloying elements similar to that of the carbon. So you know the carbon helps a lot in transformation hardening. All the alloying elements which are helping or behaving in by and large similar to that of the what you call similar to that of the carbon, so their effect is taken into account using the parameter CE. And CE is there are equations, there are multiple equations, so which are used for this calculation of which starts say chromium carbon weight percentage plus I think nickel plus manganese. I am not sure of these equations, but there is a nickel and a manganese. Let me see if I can show you. I don't remember these exactly. So, or I can share it with you later also. Where in the nickel plus manganese, I believe, and then it's I think 5. Then there is. Vanadium, molybdenum, and tungsten, I believe this is 6, and then there is a copper plus there is one more alloying. But let me show if I can show you something related with this carbon equivalent equations, which will be indicating the effect similar to that of the carbon. So here carbon equivalent is calculated using this okay, Ce is equal to C plus manganese divided by 6, chromium plus molybdenum, I think there is vanadium as well, plus nickel and the copper divided by 15. So this is one of the equations. Likewise there are multiple equations, different types of the equations which are used to calculate The carbon equivalent is affecting the CE affects the critical cooling rate, and the critical cooling rate is used as an indicator of the ease of hardening. Okay, ease of hardening. So this is one side where the hardenability or the ability to get a transformation hardened, that is a composition dependent. This is just one aspect. Another aspect is, have you thought of like what I'm saying here, you have got the say austenitic state. Okay, for a CCT diagram, here you have temperature and here you have time. Okay, so here what we are saying here, you have the homogeneous austenitic state. Homogeneous austenitic state means Fe plus say 0.3% carbon, 0.1% chromium, 0.2% manganese, whatever it has, everything has got dissolved. Then only you will be able to have the effect similar to this. If you find a situation where the chromium has not got dissolved, or manganese has not got dissolved, or the carbon is still there as an individual element, it is not going into the solution, in that case the alloying element, the CCT diagram will be different, critical cooling rate will be different. Why? Because you have not dissolved all the alloying elements. So if the limited dissolution has taken place, you will find that the effect of alloying element on the transformation will not be the same or will not be available. So which means if these effect of these alloying elements on the transformation or on the CCR, critical cooling rate, is not available, means your critical cooling rate requirement will increase. Despite of presence of the alloying elements present in the steel, if you are not able to dissolve them in the solid solution, their effect on transformation will not be available. Okay, so this is the point. In welding, what we are doing, let's say these are the two components. So this is the section that you have fused, it's fine, or that you have deformed for developing the joint. But the zones which have been heated nearby, say just for 2 seconds it was heated to 800 degrees centigrade, or this has been heated to 1400 degrees centigrade just for say 1 second. The point here I am trying to make is, you see, the high temperature exposure for short time or long low temperature exposure for long time, these are the two things. Okay, so in both the situations it is possible that you are not able to dissolve the things completely. That is one aspect. So here dissolution is more, here dissolution is less. So more dissolution, less dissolution at lower temperatures. At higher temperature things will be happening fast, possibility that things may get dissolved. So the thing which is important here is this, like 1400, 1300, 1200, 1100 degrees centigrade. These are the say 4 zones being formed. So if you see the corresponding Weld thermal cycles, they may be completely different, like this. Okay, so the thing is, your temperatures here, the heating rate, cooling rate are different, like this, at different zones, different heating and cooling rates. So high temperature exposure in this zone is for shorter period, low temperature is for longer period, further longer periods. So when you have high temperature, here you will have coarse grains, and there is a possibility that dissolution is more or less enough. Here you will have finer grains and partial dissolution. Okay, here further finer grains and the no dissolution. So if the dissolution is not happening, change in grain size is different at the different zones, So the size of the grain and the solubility of the alloying elements, these two things are very critical in welding for facilitating the transformation. Here everything is getting dissolved, so you will get the effective transformation hardening. Here partial transformation hardening, and here no transformation hardening. Okay, why? Because at one location you have completely dissolved the things because of high temperature, it got coarse, and at other locations temperatures are lower for shorter time or longer time, you will be able to see that the things are not getting dissolved completely. Okay, so the first thing is at high temperature things will be happening very fast, reactions and diffusions will be taking very fast, and therefore you may find the complete dissolution. Okay, so this is what you are going to experience. Okay, let me go here from here on itself. This I have talked earlier. Let us see this one. This is simple iron carbon diagram, you know it. So what is the temperature that you need to form the homogeneous austenitic state? That is this upper critical temperature. Depending upon the composition, different temperatures you need. If you heat higher temperatures for longer time, you will find the coarse grains. Okay, here you will have the fine grains. This is what you can only see from the iron carbon diagram. Okay, since your the weld thermal cycle being encountered at different locations is different, like this. So it is possible like this is corresponding to this location, the CR4 is corresponding to this location, CR3 is corresponding to this location, like this. So since your cooling rates encountered in the different locations are different, peak temperatures encountered are different, so at each of these locations you may find the different microstructural transformation. Okay, I hope you can relate it. So somewhere you'll have coarse perlite, somewhere fine perlite, somewhere perlite plus martensite, somewhere complete martensite, like this. Okay, so this is the reason why you get a lot of heterogeneity as far as the properties are concerned in the weld zone. Okay, here you have got say martensite complete, here you have got say 50% martensite, here you have got like, so that 50% perlite plus martensite, 100% fine perlite, 100% coarse perlite, like that. So different locations, different phases which will be formed. That is why you get a lot of heterogeneity in the properties. As far as the temperature is concerned, recrystallization temperature for steel is 400. Okay, so all the zones which are being heated above this are going to get recrystallized, and that is what you can see here from this band. Below the lower critical temperature, a recrystallized zone is being formed. Zone which is being heated to the intercritical temperature range means below the lower critical and upper critical temperature, that will be experiencing the fine grained zone. The zone which is being heated to the like say the austenitic state, this zone will be under the coarse grain heat affected zone. The zone which is being heated in the both two-phase zone, like the mushy zone where you have liquid plus the solid both, that will be falling under the partial melting zone, and the one which is heated above the liquidus temperature, that will be falling under the fusion zone or complete melted zone. Okay, that's how you can relate the welding of steel with the iron carbon diagram and the formation of the different zones. Okay, that is one. And the same thing I have shown using the another diagram. This is the center, and what you can see here, this is the liquidus one. So the partial melting is taking place here between the liquidus and solidus. So this is the PMZ zone or partial melting zone. Okay, this is the coarse grained zone. Okay, where grain growth is taking place. This is the fine grained zone, intercritical temperature region. This is the partially recrystallization or recrystallization zone, like that. This is so partially refined or refined zone, like that. So in the distills you will come across the range of the temperatures. Okay, and accordingly the structural transformations will be taking place. Okay, probably my goal is not to talk about all this. This about I have already talked about this pH thing. So my purpose of talking about all these things was not just to because we have to basically talk about the heat treatment. So what are the requirements of the heat treatment in steels? You have to have the homogeneous austenite. That is the first requirement. Okay, and based on the kind of the phases that you want, say for hardening purpose, for strengthening purpose, or for softening purpose, you have to use the different heat treatments. Say this is quenching, where you want to hardening, so you need rapid cooling. Okay, you need normalizing when you want to refine the grains and increase the strength. So normalizing heat treatment, see, moderate air cooling, or you can say air cooling. And the softening when you want to perform, like say let's go for annealing, say the furnace cooling or something like that, very low cooling rate is to be applied. So in any case, the formation of the homogeneous austenite is one requirement, followed by the different cooling rates. The different cooling rates need to be imposed as per the purpose of the heat treatment, as per the structural transformation that you need to achieve the desired properties. This is where now you'll be coming across variety of problems. Okay, this is the weld. Here you had one thing in your the transformation. Here you had another thing. In the third zone you have different. In fourth zone you had different. Okay, so now here you found say the refined is a partially refined, the refined, the coarse grain, further coarse grain, and the partial melting zone, P and Z. Okay, so the coarse grain and the PMZ, these are the say four zones. Now when you give the high temperature exposure for solutionizing purpose, high temperature exposure for solutionizing purpose, all these being of the different constituents and of the different sizes, they will respond differently. Something which is fine will respond differently than something which is very coarse. Okay, now thereafter when you give one type of the cooling rate, certainly you cannot give different cooling rates for the different zones during the post weld heat treatment. So what you can do, you will give one type of the heat treatment. So in that case, that each zone is going to respond in different ways. This is the problem. So the thing is, on heating, the different zones will behave differently, and subsequently on cooling also they will behave differently. So it is really very difficult to have the homogeneous or a homogeneity in properties, especially after the welding. This is one aspect, okay, which must be considered. Like when you perform the post-weld heat treatment like annealing, normalizing, or the hardening, the each zone will be responding differently because of the different uh, existing structures in the heat affected zone. And the weld is altogether a different thing. It may be same or the different. That will bring in the another complexity. Okay, so this is where I will stop. Maybe I'll talk a little bit more about the specific heat treatments, especially when the similar filler metal is used or completely different filler metal is used, and what we get actually from the performance point of view. Okay, because of these structural heterogeneities, the weld joint perform actually in very different ways. That is why it is very important to consider like how to design and how to execute the heat treatment. It's not easy for the weld joints. So those intricacies and difficult aspects I'll be talking in the next lecture.